Hello again, and today I'm sitting in my robe because I'm actually pretty cold for whatever reason. I think I'm a little bit ill from all of my travels lately, but I wanted to make this video because we're finally into the thing that is, in my opinion, the reason why we're using this application or packages. So we're looking at now reinforcement learning based training. And let's just pull this in real quick so we can see what's going on. So we're going to train locomotion policies, and I did test this. That in the real world, this is running on my laptop. I was able to train a policy within about 30 seconds. We're kind of making this simulation the same as the robot. And we're going to switch up the scenes to see what else is going on. But first thing that's important is you want to reset to initial pose to make sure that all the training starts from the same place. And then here is robot states and joints and all those things are stored in a buffer. We're going to execute an action, and then we're going to computate the reward, and we're going to check obviously for things like significant deviation, like robots flipped over, robots ankles have exceeded the maximum. The if we've got an IMU on board, we're going to check that kind of stuff as well. Okay, and then observation computation. This pretty obvious what that is. And here's a reward function. It's really the crux of what we're doing here. We're going to say that the robot's tracking its linear and angular velocity. The action rate, changes in action. We want the least amount of changes in action. And then in this case, these are just examples. So in this particular case, base height away from target, you want to keep the robot, on the ground. And then, similar to default, you do want the robot to stay as close to the default pose as possible. The more out of sorts it gets, trying to execute a policy, the worse things tend to be. So then we install this Legged Robots repo, and this is from, I thought I had that open for you guys, but this is from, I thought I had it open, but anyway, this is from a Isaac Gem repo. It's, kind of deprecated, and I think now using Isaac Labs instead. We're going to pip install this reinforcement learning package, and then from there we're going to install Tensorboard, which Tensorboard is kind of a place where you can see the stats of your training job. You can see them in kind of real time, and I can take a look at the various aspects if they exist. So essentially you're writing to a log file, and the log file is constantly being updated here, so you can see pretty easily what's going on. Okay, and then we're going to monitor the job as it's running, and then we're going to evaluate our policy to make sure it actually works, and it should kind of start walking, essentially. And then you can deploy in the real robot if you wanted to this reinforcement learning policy. Similarly, I have a Boston Dynamics spot at the moment, and I've done this with Isaac Labs. But I'm going to go back and do the same thing for Genesis just to make sure. I mean, really shouldn't be any different. But in the interim, we've done a lot of other things. And I kind of glossed over them because I wanted to get to this one, which is kind of the most important one. But I did go back and look at parallel simulation and motion planning and those kinds of things. And I might throw those videos in on the end. But here's what we're here for. Okay. And then command line tools, definitely going to make a video about that. So that being said, let's just take a look. First thing I did was I did do the installs. The installs are fairly easy. I don't want to gloss over it, but they were simple. And now we're into this code here. Let's move that out of the way. Okay. All right. So, yep. All right. So here we got this dictionary. In a dictionary, nothing really interesting to say there. Trying to see if there's anything worth talking about in here. These are your joints, default angles. So this is where we're going to start. These are the names of the joints. Terminate if roll greater than 10 degrees, pitch greater than 10 degrees. And the base pose, initial position, episode length is 20 seconds, resampling time 4 seconds. Okay. Here's our reward function. And let's just take a look at this. You want your base height and feet height. This is the target. Tracking linear velocity, it's 1, angular velocity 2, so we're going to stay within this angular velocity. That makes sense. You want the robot to walk in a straight line. And then in here, the number of commands we have, going to move in the X and not move in the Y. And obviously no Z axis. We don't want this thing flying. Or moving in a kind of diagonal, depending on what planes you're on. And then from here, we're going to pass those go-to walking arguments. And then this is where we're going to log all of the results, and we're going to use Tensorboard to kind of look over all those results. So I make the environment, and then I am running my policy, dumping all of the data back to this log, and these are the iterations, and we set it to max iterations, which are set up at the top, and that's it. So let's run this. And while we run this, we've opened up we've opened this up, so you can see at this location is where the Tensorboard is running. And let's bring the Tensorboard back. There we go. So as this is going, you're going to see this update. These nice images. But you can see go-to walking. And, you know, kind of what you want is you want to, as you go through the episodes, you want to see this curve kind of do that. Still going. Oh, and it's done. All right. So now that we've trained this policy, and this is you know, we should fiddle with these numbers just to see what everything does. Certainly there's a few that I would like to mess with just to play around. And then, but first let's just go ahead and now that we have the, you know, policy trained. The next step is to evaluate. So we're going to go to evaluation, run that. And this is the cool part. This is what we're all here for. I want to see the robot walking. So it's building. Oh, and I should point out that the training time was 47 seconds here. I'm running on my laptop and I'm running a lot of other stuff at the same time. And you can see there's the robot walking in a straight line as it's supposed to be. We have no obstacles in place, but we will definitely provide some obstacles at some point. This is just to prove the case. And I will find some example scenes with some great obstacles, and we'll see what we get out of those. Again, individual robot walking, we could have created thousands of these and checked our policy out. Awesome. Just to fly back through a couple things, and not going to be super specific about what's going on here, but I did want to show you what this is based on. This is Leggett Robotics, Leggett Gym, and you can take a look here and see they're shifting to Isaac Sim. They've been migrated the environment, etc. This is how to pip install this directly, but this is, again, don't need to use this anymore. Just go to Isaac Gym, it's there. Isaac Sim, it's there, excuse me. And you can see the repo is fairly old. And there's the Leggett Gym, and here's training and play. And some animals, robots that are supported. I was looking at animal, that was pretty interesting. And it's the config file for those support robots, and you can see here's joints and angles, and so this is very similar to what we already have. Here's how to do this with the URDF file, joints, and here's control, and then there's some metrics for the joints. But you can run through this now in Isaac Sim, which I'm not sure if I made a video on that. I think I did back in the day. Hard to tell anymore what videos I've made. But in Isaac Sim, you can run this same thing. Okay. Promised a little bit of play on for the very end of this video. So here's training. We're going to, let's see, completely just blow up our training job by doing something ridiculous. What do we want to do that's ridiculous? So joints. How about let's change that to 100, and let's change the linear velocity to 10. And the action rate, let's change that to 10. And then let's speed this sucker up a little bit. 1.0. 1.0. Okay. Okay. Let's see what happens when we do this. It should be fun. Okay, again, it's going to modify our Tensorboard as it gets started. Just getting going, so it's empty. As it starts to train, you'll what did I screw up? What was that? did some kind of check on my action steps. Critical angle. Oh, I don't think I did change that, but let's back it up. All I did, really all I did was just change one thing. Let's just stick in the reward functions and change those. So we're going to say, linear velocity in C. So now that can be 1. Sorry, I did make a mistake. Excuse me. Slightly ill. When you're ill, you make mistakes. Okay, now we're running, and that was totally my bad. So now you'll see we're training, and essentially all I did was just bump up the velocity. Okay, still a few seconds remaining. I don't have any witty jokes. I'm not feeling it great, but you know. And you can see here, it's still training. Okay, and now it's finished. Okay, so now let's check out our policy, which shouldn't have changed much because I didn't do much. Oh, look at that. It is not going anywhere. So I did do something wrong, and I'll have to figure out what I did. I love these one-take videos because then you can see the real errors that I make with especially NyQuil, DayQuil infused brain. But there you go. You can make some changes, whether for better or worse. They're definitely changes you can make. All right, I'm going to end this one here. I hope you enjoyed the video and look out for the next one.